Our project proposal is to use machine learning for cardiovascular disease risk prediction. Cardiovascular disease is the leading cause of death in the U.S. Key risk factors for CVD include hypertension, high cholesterol, smoking, alcohol use, physical inactivity, diabetes, and being overweight. The American Heart Association predicts that over 45% of the population will have CVD by 2035. A survey by the Cleveland Clinic found that many Americans are unaware of the health ranges of these risk factors and underestimate their own risk of developing CVD. Our team seeks to analyze risk factors to determine which are the most significant in CVD and to design a model that will determine a given individual's risk of developing CVD. To address our problem, we use various methods. We first chose a dataset from Kaggle containing detailed information on the risk factors for cardiovascular disease. Then, we cleaned our dataset by removing unwanted features and missing or invalid values. We did some preliminary exploration and normalized the features to improve the performance and training stability of our model. After feature reduction, we split the dataset so 80% of the data could be used for training and 20% for testing. Finally, we leveraged supervised learning techniques such as logistic regression, gradient boosting tree, and neural networks, and compared the performance of each method in classifying whether someone was likely to have cardiovascular disease or not. A PCA-reduced model with 12 components explained the greater than 95% of the variance. This PCA-reduced data was the model used in all subsequent models. Together, the first three components of the PCA model explain over 50% of the variance. Looking at the composition of these first three components, the first component has the highest contribution from the gender features. The second component has the highest contributions from the cholesterol and glucose features. The third component had the highest contribution from the active feature. Overall, this suggests that the four most predictive components in order are gender, cholesterol level, glucose level, and physical activity. Logistic regression was first explored to tune the parameters of the logit function for binary classification. Tenfold cross-validation to optimize the lambda of a ridge regularizer based on accuracy was performed on the normalized dataset and all the component PCA dataset. The max accuracy from normalized data training with an optimized lambda was found to be 71.2%. The accuracy versus number of PCA components was then analyzed to determine the number of such components needed to exceed this accuracy. This was determined to be 12 PCA components with an accuracy of 71.8%, as shown in the figure seen here. In order to implement a gradient boosting tree on the PCA-reduced data, the gradient boosting classifier model from scikit-learn was used. We ran the gradient boosting classifier on the training data and got an accuracy of 0.724, then scored it on the test data and got an accuracy of 0.716. We created a confusion matrix and visualized the number of correct and incorrect classifications as seen on the left. Subsequently, multiple methods of parameter optimization were used. In order to test many combinations of values, we utilized nested for loops for different ranges of each of the parameters. This resulted in a total of 1,260 combinations of parameters being tested and resulted in the highest model score of 0.713. Another method we used to test combinations of various parameters of the gradient boosting classifier was randomization. We ran 20 iterations, which produced the highest accuracy score of 0.719. Finally, we also utilized the grid search CV model in sklearn to tune the parameters. This method returned the highest accuracy score of 0.72. Thus, the grid search CV model proved to be the best method for the gradient boosting classifier parameter tuning. To build a neural network for our dataset, we employed TensorFlow's Keras library. Since the number of samples is significantly greater than the number of features, we implemented a fully connected feed-forward neural network with dense layers using the ReLU activation function. Because we were doing binary classification, we used a single output layer with the softmax function to normalize all outputs and ensure they range from 0 to 1. To train our neural network, we defined 20% of validation examples to be taken from the training set. Our initial model had a 9-551 architecture. Trained with the Atom Optimizer, a binary cross-entropy loss function, batch size of 32, and 50 epochs, we achieved an initial accuracy of 71.75. We utilized Bayesian optimization in order to tune specific hyperparameters within the neural network. We found an article online from which we based the code off of. The code used 5 folds and focused on optimizing the following parameters: activation, batch size, epochs, learning rate, neurons, and the optimizer, and the optimal values of each of these hyperparameters are shown below. When a neural network model with these parameters was tested on the testing dataset, the accuracy was 0.618. The recall and precision scores for this model were 0.276 and 0.827 respectively. The scikit-learn hyperparameter optimizer Grid Search CV was also used to find and compare the hyperparameters that maximize the accuracy of our neural network. Cross-validation with 10 folds ran on the PCA-reduced dataset to optimize activation, batch size, epochs, neurons, and optimizer parameter, as shown below. Our neural network model run with these parameters on the testing dataset resulted in an accuracy of 0.718, a recall of 0.691, and a precision of 0.720. In order to determine the best model to predict cardiovascular disease risk, the models were compared and ranked based on their accuracy, recall, and precision. The purpose of our project is to create a tool that would inform users of their cardiovascular disease risk so they can make more informed decisions about their health. In this case, it would be more important to catch a higher proportion of true positives rather than excluding false positives. Thus, the recall score of the model was determined to be of higher importance than the precision score in the rankings. Due to the low accuracy of the neural network optimized with Bayesian optimization, this model was ranked fourth. The other three models were ranked in order of highest recall scores, with logistic regression in third, gradient boosting tree in second, and the neural network optimized with Grid Search CV in first. After comparison of the four models, the neural network optimized with Grid Search CV was determined to be the optimal model for predicting cardiovascular disease risk. This model had both the highest accuracy and the highest recall, with the precision only 1% less than that of the highest precision model. The results of the principal component analysis of the data suggests that male gender, high cholesterol, high glucose, and physical inactivity are the most predictive risk factors for cardiovascular disease. However, even after optimization of parameters, each model was only able to achieve around 72% accuracy. This implies that the dataset may be insufficient to sufficiently predict cardiovascular disease risk. Additional data on risk factors, such as diet and family history of CVD or preeclampsia, may improve the model's predictions. These are our references we used for the project, and thank you for listening.